Hello everyone, welcome to the lab explanation video for Lab 2.2, Facial Recognition with Variational Autoencoders, Debiasing, and TensorFlow. In this lab, we are going to be showing how certain deep learning models such as convolutional neural networks can sometimes suffer from the issue of bias, and we will implement a type of deep learning model that advances the convolutional neural network architecture called Variational Autoencoders, as well as adding special debiasing methods to tackle this issue of bias. Bias is a very important issue in machine learning, as sometimes it can be embedded in our data, whether we intend to or not, and using debiasing methods is an excellent way to ensure that AI is for everyone. To access this lab, you can go to the inspiredk.org website and click on the AI Program Labs button. This will take you to the inspiredk.org GitHub page, where you can navigate to the MIT Intro to Deep Learning repository. This lab we're going to be going through today is implemented from the MIT Introduction to Deep Learning course, and the instructors of the course based a lab off of this paper, Uncovering and Mitigating Algorithmic Bias Through Learned Latent Structure. Once inside the MIT Introduction to Deep Learning repository, you can navigate to the Lab 2 folder and click on the Lab 2.2 Facial Recognition with VAEs, Debiasing, and TensorFlow Python Notebook to access the lab by clicking the Run in Google Colab link, which allows you to go through the lab on a Google-hosted platform where high-power processing units are available for free to anybody with a Google account. So now let's dive into the lab. First, you need to make sure that you are working with a tensor processing unit, or TPU. This can be done by navigating to the runtime, change runtime type, and changing your hardware accelerator to a V2-8 TPU. Then you can click Save and click Connect in the top right corner to connect to your TPU runtime. At the start of the lab, you can run this code block in order to see a short video offered by Google that explains why bias is an important issue. And you can watch the video. It is about 2 to 3 minutes long, and you will gain a deeper understanding of why bias is so important, especially in machine learning. So now that we have accessed a TPU and we understand bias, let's download all of the packages and dependencies that we're going to be needing for this lab. This will take about 2 minutes, so while they are downloading, I would like to go through the MIT Deep Learning package, which was created by the instructors of the Introduction to Deep Learning course for their labs. In the MIT Deep Learning package, there are several functions that are built in so they can be accessed from the lab to abstract away some of the more complex coding parts of our lab so we can focus on the deep learning experience. One of these functions is the class of training dataset loader, which we use in order to take our training dataset and correctly format it for our model to run. So inside of our model, we have the initialization where we load the entire dataset into memory and separate it into the faces and not faces. We have the getTrainingSize function to see how many training examples we have. We have the getTrainStepsPerEpoch to get the training size for a given batch that is inputted. And we have the getBatch function in order to take an input of images and a probability distribution to sample from our dataset to get different batches of training examples. Then we have the getNMostProbability faces, where we find the images that have the most likely probabilities in a given probability distribution. And finally, we have the getAllTrainFaces function to output all of the images that are faces. Then outside of our class for training datasets, we have the getTestFaces function, which extracts some example faces from the MIT Deep Learning package, 5 from each demographic and gender, to see how well our model performs on some example images. So our packages are still importing. So we first install TensorFlow 2.0, which we use for multi-dimensional arrays called tensors. We have the OpenCV-Python, or CV2, package, which we install as a dependency for the MIT Intro to Deep Learning package. and it is a framework that allows us to have computer vision tasks like ours supported. Then we import several different packages such as functools as a dependency for functions that output other functions. We have matplotlib in order to graphically visualize different statistics such as our loss. We have NumPy for NP arrays, which are multidimensional arrays similar to tensors from TensorFlow. And we have TQDM, which allows us to work with textual progress bars. So for the datasets that we're going to be using in our lab, we have the positive training data, which is the data containing faces, from the CelebA dataset, which contains many different images with a wide variety of different celebrities in different angles, different accessories, genders, and much more. Additionally, for our negative training data, which is the non-face images, we use some of the non-human categories from the ImageNet database, which contains many more images of many different types. Finally, we use a scale called the Fitzpatrick scale, which allows us to classify different skin types as lighter or darker, which we can use to see if there is any bias in our model based on the CelebA dataset. All of the images that we are going to be working with in our lab are 64 by 64 in size and in RGB format. So now, let's get all of the images from our CelebA and ImageNet databases by using the tf.keras.utils.get file in order to get all of the images from a URL. We're going to use the training dataset loader from the MIT Deep Learning package to load this dataset. This will take about 30 seconds to load our entire dataset, and when it is done, we can look at the number of images that are inside of our training dataset by using the getTrainSize function on our training dataset loader. We can also get a batch containing 100 images and their labels of face or not face to examine how our dataset has different images of faces or not faces and how much variety we are going to have. So this progress bar that we have that has a very long number to show the progress of our download is the number of bytes from our dataset, and this contributes to about 1.26 gigabytes. So now that our entire dataset is loaded into memory with our training dataset loader, we can see that we have 109,914 training images in our image dataset containing both faces and non-faces. And we can use our batch of 100 images and their labels to examine the face and not face images. As an example, we have this image of a face of a white man, whereas we have a not face image that contains an environment. If we move these sliders on the right-hand side to change different indices from our batch, we can examine different examples. At index 10 in the faces, we have an image of a woman, and at index 15 in the not faces, we have an image of a road. This shows that we have a very wide variety of different images in our dataset. Now, let's build a convolutional neural network in order to tell the difference between these faces and not faces and detect the actual faces. We're going to start by defining a variable called nFilters and set it to 12 as a factor for the number of different convolutional feature maps we're going to have throughout each convolutional layer in our CNN. Then we are going to use the TensorFlow built-in layers in order to define some of the layers that we can use to create our entire model using the sequential API. First, our convolutional layer will be based on the Conv2D layer built into TensorFlow, and we will by default set the padding to same, where each image will automatically be set to the same size, and we will by default use an activation function of rectified linear unit, or ReLU, which is commonly used for computer vision tasks like ours. Additionally, we will define a batch normalization layer, which instead of pooling, sets all of the values to a similar scale so they all contribute equally to the next layer. Then we have the flatten layer, which turns any two-dimensional or more input that it takes into a one-dimensional output. Finally, we have a dense layer, which is based on the built-in TensorFlow dense layer, and by default will have an activation function of rectified linear unit or ReLU. Now let's use the sequential API in order to define our model. So in our first convolutional layer, we're going to have 12 feature maps, which is at a scale of 1 for our factor of learned feature maps. And we will use a kernel size of 5 by 5 to learn the different features. And we will take the input from our convolutional layer, pass it through, and then send that through a batch normalization layer. Similarly, in the second convolutional layer, we will now learn 24 feature maps, still with a kernel size of 5 by 5, which is a factor of 2 from our original number of filters of 12. Then in the third convolutional layer, we learn 48 feature maps, now with 3 by 3 kernels to capture more deep representations in our data. And finally, we learned 72 feature maps in our final convolutional layer, still with 3 by 3 kernels. And we take the batch normalized output from that final convolutional layer, and we pass it through a flattened layer to turn it into one dimension. We pass that one-dimensional output through a dense layer or fully connected layer with 512 neurons, and then pass those finally through our last dense layer, which takes an input of n outputs from our function and dictates how many outputs we will have with no activation function, as these are our final classifications. Now we're going to build our standard CNN classifier using the default value of 1 output for binary classification as face or not face, and we will pass an example image to predict for the model to initialize it. When we run this code block, we can also use the .summary function on our classifier to examine what the different layers are going to be outputting. Our first convolutional layer takes a 64 by 64 image, and it turns it into 32 by 32, as each convolutional layer is halving our image size, and we learn 12 feature maps. Then the batch normalization takes the same output shape as our convolutional layer, and in the second convolutional layer, we have our image size again to 16 by 16 and learn 24 feature maps. In our third convolutional layer, we have our size again to 8 by 8 with 48 feature maps, and finally in our last convolutional layer, it is 4 by 4 with 72 feature maps. This is allowing us to take our high-dimensional image of 64 by 64 and compress it into a smaller shape of 4 by 4 that has more dense information through the entire 72 feature maps. Then our flattened layer takes the final convolutional output and turns it all into one layer and passes it through our dense layers to get our final predictions. Now let's take our standard CNN and use our training process in order to optimize it on our training dataset so it can have a high accuracy while classifying. First, we're going to set our batch size and learning rate in a hyperparameters dictionary to keep them constant throughout our entire training process. And in my case, I use a batch size of 64 and a learning rate of 5e-3. I highly encourage you to experiment with these values as well as the optimizer that uses our learning rate in order to see which one allows you to get the highest accuracy. Then for the optimizer, I used Adagrad, as out of all of the optimizers I experimented with, it seemed to work the best with my set learning rate. And we can also find other optimizers that you can try at this link that is provided inside the lab. Then we're going to define a loss history list, which will contain all of our losses for graphing purposes, and we can create a plotter called periodic plotter from the MIT deep learning package that constantly updates while we train. Finally, we can use TQDM in order to clear any of the previous progress bars we may have, so they do not affect our new progress bar to track the progress of our training. Now we can define a function that will be run at every training step for our model, where it uses the TensorFlow GradientTape method in order to compute the loss and then compute a value called the gradient that can be used with our optimizer to lower our loss. So we are going to take an input of x and the expected outputs of y, and we will find the predictions from our CNN for those input images and compute the loss using the sigmoid cross-entropy loss based on our expected outputs y and the predictions logits. We use sigmoid cross-entropy as we are having a binary classification task, and sigmoid functions automatically flatten any values greater than 1 to be between 0 and 1, which is perfect for our binary classification. Then, based on our loss value, we can compute the gradient of the loss function with respect to our input, and we can use that gradient value with our optimizer to apply the gradients to the model and achieve a lower loss. We are going to run this training step function for every possible batch inside our entire training dataset, where we will get a batch from our training dataset, and we will pass it through our training function to get the loss and update the gradients, and then we will get our loss history and append the loss value we have to it and plot the loss history loss to see the trend that we have. Finally, when we are done training, we will print the final loss to see how well our model performed. Our training process is going to take about 3 minutes, so at this point, I would like to take an opportunity to go back through what we've done so far. So at the start of the lab, we saw that we have a video teaching us about different biases in artificial intelligence, and we saw how machine learning can sometimes be affected by these biases, so it's extremely important to use debiasing methods to resolve this issue. Then we connected to a tensor processing unit in order to have high-speed computations as well as fix certain issues with the built-in TensorFlow T4 GPU, and we installed all of the relevant packages and dependencies that we need for our MIT deep learning package as well as others. Then we installed our dataset from a provided link, and we used the MIT deep learning package's training dataset loader in order to store our dataset in memory and have several built-in functions to work with our dataset. The images of faces that we used were from the CelebA dataset, which contains many different varied faces of celebrities, and our non-face dataset was ImageNet, where we took several different images from non-human categories, and we compiled them together with our faces to create one training dataset. Finally, we used the Fitzpatrick scale in order to measure the different skin colors of our faces to see if racial bias is affecting our model. We then took our dataset, which is now loaded into memory, and we examined some example faces and not faces images out of a batch size of 100 from our entire 109,000 images in the training dataset, and we saw that there is an extreme variety of faces and not faces for our training dataset. Then we created our convolutional neural network in order to detect different faces by first creating a factor of the number of feature maps that will be learned, and progressively scaling up how many feature maps we learn while decreasing the size of our images through all of 4 convolutional layers until we reach a very small dimensionality with a lot of represented dense information. And finally, we flattened that convolutional output, sent it through several dense, fully connected layers to get our binary classification output. Then we examined how our model has different layers that each output in different shapes, where each convolutional layer is having the output the input that it took into a half of its size. And finally, we created our training process in order to have a set batch size and learning rate using an optimizer of AdaGrad and having a train step function with the GradientTape to compute our gradient value and update the weights based on that gradient so we can optimize our model towards lower loss and higher classification accuracy. Now, after 3 minutes and 3 seconds, our model has finished training with a loss of 0.007, which is extremely low, meaning our classification accuracy will likely be very high. As we can also see, our model very quickly achieved a lower loss and continued to progress to a lower loss until the end of its training. Now, let's evaluate the performance of our model on the training dataset and see how it performs on some examples of different demographics. So first, let's get a random batch of 5,000 images and their labels from our training dataset, and let's pass them through the model to get our predictions and convert them to a binary format using the sigmoid function, and then computing the amount of predictions that were right versus the amount of predictions that were wrong to get our accuracy value and output it in the console. This takes a few seconds to perform. We can see that our accuracy is 99.3%, which is extremely accurate. Now, let's use the getTestFaces function from the MIT Deep Learning package, which includes faces that are light females or lighter skinned females, light males, dark females, and dark males. Each of these classifications will have 5 different test images, and as we can see, there are different orientations of the face as well as different lightings that we experiment with through these faces. We can take all of these images and we can pass them through our classifier to see how well it does for each demographic and what classification it provides. So we can pass each of these 5 faces for each of our demographics through the model one at a time to get all of the classification probabilities, and we can plot the accuracy of our classifications in a bar chart. We can see that for our light females and light males, we had a significantly higher accuracy than the dark females and much more than the dark males. This shows how our dataset, by random chance, is sampling more on the light faces of females and males compared to the dark faces. We can resolve this issue by creating a debiasing algorithm that, as we are training, automatically samples more from the underrepresented demographics in order to equalize our training accuracies for all demographics and as well as other biases that may be occurring. So this is where the variational autoencoder comes in. The variational autoencoder takes an example image as input, passes it through an encoder network, which is similar to the convolutional neural network we just defined, computes a mean and standard deviation vector, which is turned to a type of space called the latent space, where it contains different latent variables, and these latent variables contain very dense information about our image, including several different demographics or undersampled representations that we can use to see which images are not having as common latent variables, and taking those less common latent variables to resample them more often. So we have our latent space, and we take random samples from it through our decoder network, which does the opposite of a convolutional network and takes our dense representation to another image, effectively regenerating a new sample. Now, let's start by defining our variational autoencoder loss function so we can use it in combination with several debiasing methods to create our debiased variational autoencoder. The equation for our variational autoencoder combines 2 different values, the latent loss and the reconstruction loss. Our latent loss is the loss from our latent space, which is also called the KL divergence, or Kullback-Leibler divergence. And the reconstruction loss compares the difference between our input and the output, which is called the reconstruction, and we can take this latent loss and multiply it by a value to give it a different weight depending on how much we want to weight our latent loss, and then we add the reconstruction loss to it to get our final variational autoencoder loss. So now let's define this variational autoencoder loss in code, taking an input of the input images x, the reconstructed output of x recon or reconstructed, the means from our latent space called mu, the log of the standard deviation called log sigma, and the weight for our latent loss, which is the c value in our equation, but called KL weight in our case. Now we can define our latent loss based on the equation above, where we have our log sigma, we have the square of mu minus 1, and the log sigma again. We take all of these values, sum them together for a given latent space where we have all of our latent variables, and we take that entire sum and turn it into half. Then for our reconstruction loss, we take our input and our reconstruction and we subtract them and find the reduced mean, which is the mean of our values and our output, in order to get our reconstruction loss. And finally, we get our VAE loss by multiplying the latent loss by our KL weight value, which is the weight parameter, and adding the reconstruction loss to that value. Now we have our variational autoencoder loss. We need to define the reparameterization trick, which allows us to sample from our latent space. In our example, we are going to use a standard Gaussian distribution, which looks similar to this image, where everything is centered around the point 0, 0, and our distribution is approximately circular, and everything is clustered. We are going to experiment with different values and see how, if we set certain values too high, our space will be too far and not closely related enough around our 0, 0 points, and our distribution will not mean much. Whereas if we set certain values too low, everything will cluster together and our representation will be exactly the same for our generation as it is for our input. Now let's define the reparameterization function as sampling, which takes the mean and log of the standard deviation from our latent space and finds the shape of our mean, which is the batch size by the latent dimensionality, and gets our standard Gaussian distribution using tf.random.normal. We pass in a shape parameter, which is the shape of our mean, so we can correctly multiply that Gaussian distribution by the exponential of half of our log sigma value, which is the log of the standard deviation, and we can add our z mean, which is the mean of the latent space, to get our reparameterized computation. Now that we have these two critical functions defined, the loss function and our sampling function, we can create our debiased variational autoencoder. This diagram shows how we take our input data, pass it through some certain probabilities to get a sample, and have that as our input, where we pass it through the encoder, get binary classifications, which we can use on their own, and we also get a latent space. We can use this latent space through our decoder to get our reconstruction. We can also take our latent space to update the probabilities for sampling from our data to actively change the inputs as we are training, so that way we can sample more of the underrepresented images. Let's start by defining our debiased variational autoencoder loss function, which takes an input of the actual input x, the reconstructed input x prediction, the actual label face or not face y, and the predicted labels y logit, as well as the mean of the latent space mu and the standard deviation log of the latent distribution log sigma. First, we are going to compute our VAE loss using the previously defined variational autoencoder loss function, inputting our inputs, the reconstruction, the mean of our latent distribution, and the log of the standard deviation of our latent distribution. Then we are going to compute a classification loss using the sigmoid cross entropy loss that we used previously with our CNN to compare the expected outputs versus our predictions. Then we're going to create a face indicator, which marks the images that are faces and does not mark the images that are not faces, by seeing which ones from our expected outputs had a value of 1 in the binary classification, which represents face. And finally, we take these three values we defined to add our classification loss to the face indicator multiplied by the VAE loss, where the VAE loss is now only represented for the images of faces, and we take that sum and pass it through tf.reduceMean to get our total loss, and we output the total loss in addition to our classification loss in order to train the classification algorithm, as well as the generator itself, the VAE. Now we are ready to define the debiased VAE architecture by creating a decoder, as we can use our standard convolutional neural network as the encoder. So we are going to again define the number of filters that we are going to have as a factor as 12, We can also define the dimensionality of our latent space to be 100, representing how much compression our images will go through. So we're going to now define all of the layers that we're going to use, including the Conv 2D transpose, which is the exact opposite of a convolutional layer, as convolutional layers take a large dimensionality and make it smaller, whereas the Conv 2D transpose takes a small representation and makes it larger. We define it similarly to our convolutional layer, however, by setting padding to same and activation to ReLU or rectify linear unit. The batch normalization, flatten, and dense layer are the same as before from our CNN, with the dense layer having a ReLU activation and the batch normalization and flatten layers being as their default from TensorFlow. We also now have the reshape layer, which takes inputs and converts them to a different shape or dimensionality. Now we can use all of these layers we defined to create our decoder by first starting with a dense layer, taking our latent space and converting it to a more representative feature map, and then we can use reshape to take each feature map gotten from our dense layer and provide each with its own space in the neurons. And at this point, we have 72 feature maps from our convolutional neural network. So we start with 6 times our factor of filters, which is 12. And now we can use our transposition convolutional layers to go in the opposite direction as our convolutional network by going from the 72 feature maps to our 48 feature maps to 24 to 12 and finally to 3, as we want to have one channel for R, G, and B, which is 3 channels. And we can also reverse the kernel size, which starts at 3 by 3 for our first 2 layers and then goes to 5 by 5 so we can capture more structure in our generation. And finally, we have our output as the new generated image from our last transposition convolutional layer, and we have our decoder. Now, we can define our class of the debiased variational autoencoder and base it on the default TensorFlow model. We can start with our initialization function, which takes an input of our latent dimensionality to have the same latent dimensionality throughout our entire DB-VAE, and we can also set the number of outputs from our encoder by multiplying our latent dimensionality by 2 and adding 1. Note that we are also going to have latent dimensionality is equal to the number of latent variables learned. So if our latent dimensionality is 100, we will learn 100 latent variables. Now we can define our encoder and decoder by using the encoder as our convolutional neural network, passing in the number of encoder outputs we want to have, as well as our decoder using our newly defined decoder with no inputs. We can define the encode function as taking an input of x, passing it through the encoder, getting our predictions in a binary format, and then finding the mean and log of the standard deviation for the latent space based on our encoding, and returning the predictions, the mean, and the log of the standard deviation. We can also use the reparameterize function, which takes in the mean and log of the standard deviation and passes it through our sampling function to return the latent space, sampled with specific latent variables. Now we can define our decode function, which takes the sampled latent space and uses our decoder to find the reconstruction and outputs that reconstruction. We can combine these 3 functions into the call function, which uses the encoder to get our predictions, mean of the latent space, and log of the standard deviation of our latent space. And then we can take the mean and log of the standard deviation through our reparameterization to get the sampled latent space. And finally, we can get our reconstruction using the decoder. We finally output the predictions, latent space, and reconstruction from all of these operations to have our calling function. Finally, our predict function takes an input of x and passes it through our encoder only, and also only returns our predictions as the form of y logit, so we can, if we need to, take an image of faces or not faces and classify it using our DB-VAE to get the predictions in binary format. We now are going to define some functions with our DB-VAE that we can use for the debiasing to get the mean of our latent space, and then resample using another function to change the probabilities based on that mean for resampling of the less common faces. So we're going to start by creating a function to get the mean of our latent space, which takes an input of specific images, which will be our training dataset. The DB-VAE, we want to get the means for the latent dimensionality, and the batch size, which is by default set to 1024. We are going to be outputting the mean of our latent space by first finding the number of images we have and creating a default multi-dimensional array containing all zeros that we will update continuously to have our mean. This is going to be in the shape of all of our images by the latent dimensionality, so each image has a representation for every latent variable. Then we're going to randomly sample batches based on our batch size from our images, pass them through our model, and get the mean of the latent space for that batch and add it to our overall mean to finally output the entire latent space mean. Then we're going to use the getTrainingSampleProbabilities function that we're going to define, where we take our images, DB-VAE, and latent dimensions, now with a new variable called bins. This represents the number of classes that we are going to have for our latent variables and probabilities. So we can set each different latent variables to different probabilities of resampling. We're going to start by getting the latent space mean for our images, the DB-VAE, and our latent dimensionality, and then we're going to initialize the predictions, the probabilities of our resampling as a multi-dimensional array containing zeros to be the same shape as our means. Then we're going to loop through every latent variable in our latent space based on the latent dimensionality, and we're going to get all of the means for our given latent variable we are currently on. Then we're going to create a histogram using our latent distribution for our variable and set it with the number of bins that we define. This will give us a histogram density for each of our bins as well as the bin edges. Now we're going to set the edges of our bins to be infinite so that way we can have any possibility of our probabilities. Then we're going to use the np.digitize function, which is from NumPy, to take our latent distribution with the bin edges so we can find what part of the distribution that every data sample inside of our images dataset falls into. We can then smooth out the histogram so all of the probabilities of each of our bins sum to 1, and we can invert that smooth histogram by taking the 1 over that smooth density. We can again normalize all of these inverted probabilities by converting all of them to the probabilities that will all sum to 1. And finally, we can find the maximum between our new probabilities and the original probabilities that we had before the sampling for our latent variable to see which one is larger. After all of the latent variables have been sampled and they have been updated for our latent space, we can now finally normalize the new probabilities we have by taking it and dividing it by the sum of all of our probabilities, so all the probabilities sum to 1. We can finally output these probabilities for our resampling. Let's now define the training process, which is going to take about 6 minutes to train, so while I'm explaining, I will allow the model to train. First, we start by defining our training hyperparameters as we did before, with our batch size, learning rates, and now latent dimensionality, which we can change to change how many latent variables are learned, as well as how much our model is compressing the images it passes through. I set my batch size to 32, the learning rate to 3e-1, or 0.3, and our latent dimension to 150, as I found those variables worked the best for me. However, I again highly encourage you to experiment with the different hyperparameters to see which can get you a better accuracy. Quickly, I'm going to see why there is an error in our training process. And it seems that I did not define the debiasing loss function as I forgot to run that cell. So I'm going to go back to the top and run this debiasing loss function, and now the training process will be able to work correctly. Now we have defined our training hyperparameters, we can define our optimizer, which I again use as added delta with our learning rates, so we can use our gradient values to optimize the model. I again highly encourage you to see what other optimizers you can try with different learning rates to see if you can achieve higher accuracies. Similar to before, we define our loss history list and a plotter with the periodic plotter so we can track the progress of our loss as we are training, and we can clear any previous progress bars for our training so we can track this new training progress without any interference. Then we can create a new DB-VAE model with our set latent dimensionality, and we can define a training function for each of the training steps we're going to have. We use the TensorFlow GradientTape method, and we pass the inputs x through our DB-VAE to get the predictions as y-logit, the mean of the latent space as z-mean, the log of the standard deviation as z log sigma, and the reconstruction as our output as x-recon. We can then use our debiasing loss function with all of these values we received, in addition to the x images, input images, and y expected outputs to get our total loss as well as our classification loss. We can then take that total loss and compute the gradient value based on that loss value and use those gradients with our optimizer to change our model's weights and optimize towards a higher accuracy and lower loss. Then we can get all of the training images that we have that contain faces, as we want to debias our model for faces, and training on the non-faces would not be necessary because we do not need to debias for not faces. We can now take our get training sample probabilities to take our images, the DB-VAE, and the latent dimensionality, so we can get new training sample probabilities based on our loss value, and then for every possible batch in our training dataset, we can get that batch with our new training sample probabilities, compute the loss using our train step function, and record the loss for plotting purposes. The reason that this get training sample probabilities function is so important is because when we are sampling for new inputs, we need to make sure that the underrepresented demographics, such as images with a hat on, or glasses, or darker skin color, can be sampled more often, so our model correctly identifies faces of any color, any orientation, and it can be extremely dynamic. Finally, when we are done training, we can see the final loss value we achieved to see how well our model performed. We are approximately 40% through our training process, and we are achieving a very low loss already. So while it is training, I would like to go through a review of what we've done so far. So first, we started with downloading our dependencies and packages and examining the dataset that we have, including the CelebA dataset for faces and the ImageNet database for not faces, and we defined our simple convolutional neural network for this facial detection. We had 4 convolutional layers and a binary classification output, and we trained our model to achieve a final loss of 0.007, which seems to be extremely accurate. Then we evaluated the performance to find the accuracy of our model with a batch of 5,000 images, and we saw that it had an accuracy of 99.3% on our training set. We looked at some examples of different demographics and genders, including light and dark and female and male, and we saw that our model was actually underperforming on the dark males and dark females, not as much as the light females and males. So we decided to use a variational autoencoder in order to train our model with less bias, so all of these probabilities can become more equal. We started by defining our variational autoencoder loss, including the Colab Leibler or KL divergence, and also the reconstruction loss based on the reconstruction output that we received from our VAE. We added these losses together, and we gave a weight to our latent loss, or the KL divergence, so we could receive our final VAE loss. Then we defined our sampling or reparameterization trick in order to sample different parts of our latent space to get specific latent variables to train on using a standard Gaussian distribution, so all of our variables in latent space are correctly associated and defined together. Then we started with our debiasing variational autoencoder, or the DB-VAE, where we take our latent space variables and we use them to change the probabilities of sampling to get less bias in our dataset to train equally on all different faces and all different demographics. Then we created our DB-VAE loss function using the VAE loss as well as the classification loss based on our predictions from the model, and we performed several operations on these values to achieve our total loss. We created our DB-VAE architecture by defining the decoder part of our network, where the encoder is our standard convolutional neural network, which takes our high-dimensional output, turns it to a low-dimensional representation, and our decoder does the opposite, taking that low-dimensional input and turning it into a high-dimensional new generated output. We created a class called DB-VAE to combine our encoder and decoder, creating a function to run the encoder itself, a function to reparameterize using the sampling function, and a decoder function to run our decoder to get the reconstruction. Then we created a call function to combine all of these to take an input of X and have our reconstructed output Y, as well as predictions for the image classification. Finally, we defined a prediction function to only pass our image through the encoder and see its predictions in binary format, if it's a face or not a face. We then created a function to find the mean of our latent space, and another function that used that mean from the latent space to create new training sampling probabilities to sample from our training dataset equally for all different faces. And finally, we trained our model using these new sampling probabilities with a added delta optimizer and our debiased VAE. And now, after 6 minutes and 57 seconds, our model has finished training with a final loss of 0.08 approximately. We can now evaluate our DB-VAE on the testing dataset from before with our standard convolutional neural network, and we can create a bar chart to compare the classification probabilities from our convolutional neural network in comparison to the new DB-VAE. We can now see that the light females and light males stayed approximately the same, while our dark females and dark males are now much higher. So our model has less bias, and all different demographics and genders are now more equally represented for our facial prediction. In conclusion, we created a debiased variational autoencoder, or DB-VAE, in order to solve the problem with our convolutional neural network, where it was sometimes biased in its classifications. Although this bias was not intentional, we were able to build our model to correctly solve this problem and have our model work for everyone. So while going through this lab, I highly encourage you to experiment with the different learning hyperparameters such as learning rate, batch size, latent dimensions, and the optimizers, so you can see if you can achieve a higher accuracy and even less biased model. Again, to access this lab, you can go to the inspiredk.org website, click on the AI Program Labs button, go to the MIT Intro to Deep Learning repository, navigate to the Lab 2 folder and the Lab 2.2 Facial Recognition Python Notebook, and click on the Run in Google Colab link to go through the lab and experiment as much as you want. Thank you for joining me in this lab explanation video. Goodbye!